So yeah, first let me thank the organizers and all of you for being here. It's been a really fun day and a half so far. So look at this title. How lame is that, right? Like that's essentially the title of the workshop, because I didn't know what to say for my title. I didn't know what I was planning on talking about, and then so I sent this in, and then so then I was talking to Sophia, right, I guess on Sunday before it started, and she's like, "Oh, you're probably going to talk about the quantum stuff, right?" And I was like, "No." And she's like, "Oh, I'm not talking about that either." So we kind of like orthogonalized against each other. So this title is kind of misleading. This shouldn't be "and quantum," or I should cross that out. I'm really not. I'm only going to be talking about some of the classical stuff that we've been doing. And when I say classical, again, I'll try to clarify what I mean, because this is also quite confusing in the literature. Okay. Before I get started, I want to tell you or acknowledge some of the people involved in this. So this is work done by originally Vibin Abraham, who was a graduate student in our group, and now he's a postdoc with Dominika Zagid at University of Michigan. And then the more recent work is from Nicole Braunscheidel, who's a graduate student in my group. And then I have some slides at the end. Okay, so yesterday somebody said that they wanted to, I forget who it was, mentioned that they wanted to see a competition of who could get through the fewest slides. Oh, there you go. Yeah. So I want to continue that, and I want to see if I can beat you. Now, the reason is that I haven't finished my slides. So the slides at the end, they're not really done. So if you ask me a whole bunch of questions, I'm going to be like grudgingly like, okay, but like I'll kind of appreciate it. But anyway, so that the slides that, what did you say? That's well. This is actually I think embedded in here is a solution to a problem I've been working on for a while. So I don't know. Well, we could talk about it. I don't know. We'll see. But the final slides are actually work that Arnav has been doing. So we'll see if we get to it. But I'm not sure. Okay. But yeah, feel free to ask questions throughout, because I would much rather you walk away with a general understanding of what we're trying to do, kind of the goal of what we're trying to do, as opposed to seeing all the details and the results that I think are cool. Okay. So I'm a computational chemist, and so we were just talking about this outside, and a lot of people throw this term around. Are you a theoretical chemist, a computational chemist, applied, whatever this means? So computational chemistry, I kind of view this as just any kind of computational investigation of a chemical phenomena, some kind of computational investigation of chemistry problems, and I generally think of this as being broken up into either simulations. So if you're in the kind of quantum computing space, then you hear the term kind of chemistry simulations all the time, but most of the time they're not actually simulations, it's modeling. We're looking for the ground state, time-independent properties. Sometimes they are proper simulations, but in general, we try to kind of talk about simulations or which are time-dependent versus modeling. And so I'm an electronic structure theorist, and so I'm generally interested in time-independent structure of the electrons. I have not done much on nuclear kind of nuclear structure. When I say nuclear structure, I mean arrangements of the nuclei in the molecular systems. And so we generally are concerned with the electronic structure. Okay. So yeah.
Are there not many discussions about non-equilibrium electronic structure theory?
Oh, so okay. So.
Within the quantum chemistry community?
Yeah, so there are, I mean, not nearly as much as what you would find in like physics, but people have asked these questions. These are very kind of like coarse-grained, the typical definition for what these things are. This is definitely not excluding, excellent work and trying to model kind of dynamic out of equilibrium. We just heard a talk on non-equilibrium systems, and I'm not excluding that, but this is generally what we're talking about when we use these terms. Is that good? Okay, so actually I'm curious. Raise your hand if you're a computational chemist, quantum chemist, theoretical chemist. I know that we have some in here. Okay, yeah, there's a good sampling in here.
I always wondered.
Yeah,
I have been looking for internship opportunities, and many websites put this criteria of computational chemistry. but then they become like very specific and they just put DFT and everything else, but not that quantum chemistry. So I always wonder whether I'm a quantum chemist, theoretical chemist, or not.
Yeah, yeah, exactly. And what I would say is, be whoever the hell you want to be. So most of the time we're going to be, like in our field, whether you're doing DFT or more kind of ab initio type simulations, we often refer to this as quantum chemistry, which has been perfectly fine up until a handful of years ago when quantum computing decided to enter into the game. And now if you say you're quantum chemistry, that really, it sounds like you're talking about quantum computing, but you're not. So now we really kind of need to be talking about, are you doing classical quantum chemistry or quantum chemistry? It doesn't, it's dizzying. And but ultimately, it doesn't matter. And so if you're, sitting here looking at internships and you see, okay, it's computational chemist. Do I apply to the? Just apply, and then let them sort it out, right? So okay. So what I was going to say? Yeah. So okay, I'm an electronic structure theorist, and so that means that we run calculations on the electronic structure. And so you may think, what types of questions would you be interested in answering? And so for that, I just kind of dug through my past, and I pulled up a paper that I wrote when I was a graduate student where we ran a bunch of DFT calculations, just as an example of a kind of a typical example study that you might be interested in as a computational chemist or theoretical chemist, quantum chemist, whatever you want. And so in this case, right, we had our experimental collaborator, Caroline Gerald, and she had these really nice negative ion photoelectron spectra that she had not calculated, measured in the lab like a proper scientist. And so she measured these things. And so what you get out here is you get some kind of electron binding energy, and you know how heavy the molecules are that produce that spectra. And but they don't know what those things look like or how they come about. And so then we ran a bunch of DFT calculations to kind of, explore the different reaction energy landscapes that you might kind of run into, and we can then use this to then provide some predictions of what these actually look like. So what do those molecules look like, and why do they have this particular arrangement? And so this was just DFT calculations, and then we can kind of probe doing some kind of bonding analysis, kind of an analytic or more qualitative type descriptions of the wave functions that we get out. And so this combines a lot of different aspects of electronic structure theory, but it's all relatively straightforward. So this was like a pretty conventional study that you might engage upon if you're working with an experimentalist. And the reason why we could do this is we were using DFT, which is a pretty kind of relatively low accuracy method, but because the systems we were studying were relatively simple and the accuracy that we needed was relatively low, it worked out perfectly fine. But that's not always going to be the case. And if we just kind of look to something much more interesting, like this oxygen evolving complex that sits at the kind of chemistry engine inside of photosynthesis. Here we have this manganese oxide core, which is, if you know anything about chemistry, this just looks disgusting, right? Try to draw a Lewis structure, try to assign oxidation states. We still don't know what all the oxidation states are as you move through this catalytic process. And this is the nature's way of oxidizing two water molecules and giving off an O2 molecule. So this is a complicated system, but one of profound importance, right? If we could mimic this, we could do a lot of very interesting energy-related tasks. But this is difficult, and DFT doesn't really provide an accurate enough approach. And so this system, along with many others, we'd like to be able to have more accurate computational chemistry approaches to be able to study and answer these types of questions, like how many electrons do all those manganese atoms have? Now, if you're a chemist, you may also scoff at that question because it's not a question. There's no observable that's associated with that, but we'll still ask it anyway. And how would we answer that question? Well, we would recognize that this is a quantum mechanical system, and so we would then just go in search of the lowest energy eigenstates of the electronic Hamiltonian. And the electronic Hamiltonian is written down here, And Sophia gave a very nice kind of description of where this Hamiltonian comes from yesterday morning. And so here we just take our kinetic energy, Coulombic interactions, and so forth, which acts on a continuous space, and we discretize that space, expanding it in a single particle basis, and writing it in second quantization, and we have it written here. And I've kind of drawn the two electron interaction in red just to emphasize that it's ugly. And it's the thing that we really need to care about. That's the thing that makes this a hard problem to study. But I guess I shouldn't paint it in a negative light, because that's actually like why my kids can eat, right? Because this is difficult, I have a job, and we can continue kind of investigating how to best model these types of systems. So okay. This is if you're used to condensed matter Hamiltonians, this is a pretty ugly Hamiltonian because it's got into the 4 terms in it. But that's not, that's more of an annoyance. The real bottleneck is the fact that it acts on an exponentially large space. So if these are spin orbitals, then it's 2 to the n. If they're spatial, it would be 4 to the n. And so it's the dimension of this space that makes this a hard problem. And so, this wouldn't be a big deal if we only, if the problems that we cared about only had about 10 orbitals in them, then we could just do exact diagonalization and not worry too much about it. Except, if we look to on the previous slide, that oxygen evolving complex, some typical DFT calculations on those types of systems would have like 1 to 2,000 orbitals in them. And so you're not going to be computing those exactly anytime soon, ever, if you're talking about classical computation. Now, this isn't the end of the road because, not all the orbitals we have to treat exactly. And so, generally what we can do is use our chemical intuition to identify a certain number of orbitals that are kind of responsible for some of the qualitative features that give rise to the chemistry that you're observing. And then we treat those orbitals exactly in the presence of a mean field description of the rest of the system, or perturbative, or whatever. But the kind of exact treatment is limited to a small number of orbitals that we call an active space. Now, this isn't the only way that you can make progress on the electronic structure problem. It's one way, but it's the only way I'll talk about today. So, so we have an active space, which is just a small number of orbitals that we've kind of manually extracted to create a small Hamiltonian that we care about. And I just wanted to give you an example of what that might look like. That image rendered pretty ugly, but so if we have a dichromium compound here as an example. So in this case, we've got a chromium atom here, and these are both in their oxidation state of 3, which for these atoms have 3 unpaired electrons on each one of those chromium atoms. And so these chromium atoms are kind of like interact with one another, both through space and through these types of bridging ligands here. And some of the questions that you may really want to answer about these types of systems is if I have 3 unpaired electrons on this atom and this atom, that gives me, generally, it's going to be an s = 3/2 spin. And so if I have 2 s = 3/2 spin, they can couple to one another in a variety of ways. And then we can put them together. We have our Clebsch-Gordon coefficients for how those would couple into overall spin states. And we would like to know both the qualitative coupling. Is this going to be a ferromagnetic, meaning is the ground state going to have a net magnetic moment or not? And so if that's the case, then that's kind of answering the qualitative picture of what is the ground state spin. But we would also very much like to know what the gap is between those different spin states. And that's a quantitative picture. That is a quantitative question. And we'd like to be able to answer all of these. Now, if we just kind of plug in a very modest basis set for this molecule, we have almost already about 700 basis functions here. So we can't treat this all exactly. However, the way I described the system was that we have 2 chromium atoms, each with 3 unpaired electrons on them. And so, then you say, okay, well, let's only consider those chromium atoms. In particular, if we use our chemical intuition, we know that those electrons are going to be sitting in d orbitals. And d orbitals come in sets of 5 because they're L = 2 angular momentum eigenstates. And so then they say, okay, well, we've got 5 d orbitals here, 5 d orbitals here. We can construct an active space of 10 orbitals. And we could solve the problem in that space, no problem. That's a trivial exact diagonalization problem. And if you do that, you'll get the qualitative answer correctly. You'll find that it's a singlet ground state. So that means that these are antiferromagnetically coupled. And that's fine, except that you won't have a quantitative description of the strength of that coupling. And so if you want to do that, then we need perhaps a bit more chemical intuition and expand this active space. So in addition to our 3D, we would need to add some kind of higher functions here, this 4D, also add orbitals on the bridging ligands. And so this can easily get up to like now 38 orbitals with 32 electrons in it. And this is far beyond what is tractable with an exact diagonalization. Okay, so yeah.
Is intuition the only way to extract these orbitals?
It's not. Yeah. So lots of people, especially recently, have been kind of coming up with different automated processes for determining and identifying active spaces for problems. So I know Chris Stein and Marcus Ryer's group had developed a approach, and I know other people have, and I apologize for overlooking their work, but there's a lot of different techniques that you could use to do this. And so, historically it's been just chemical intuition. But as we have kind of better methods for solving larger active spaces, hand picking out 38 orbitals is pretty tedious. No one wants to do that. And so the reliance on these kind of automated techniques is growing, and they become more useful as the active spaces get bigger. Great question. Anything else? Yeah.
Can you also not find like self-consistent way to find the active space?
Yeah, so I think that kind of relates back to this question of kind of like, automating this process, like maybe you kind of grow the active space, you have some approximate calculation in there, and then you identify that some of those orbitals never get occupied, so you kind of shed those, add new. So there's probably, I don't know the technical details of how those automated processes work, but I assume that you could kind of devise something that uses some self-consistency to try to improve the definition of this. That's a good question. Anything else? All right. So, okay, so as we kind of move from this qualitative picture to a quantitative goal, our exact diagonalization becomes intractable. And so, this is really where quantum computing shows up as kind of interesting ways of demonstrating some kind of useful near-term quantum advantage. And the reason is that this kind of exact diagonalization in this classical setting kind of runs out of steam at around 20 to 24 orbitals. And it's easiest to think about this just as simply the memory bottleneck, right? So if you're trying to do this in a brute force way, then you really can't go beyond this. And so that makes these kind of active space models really nice targets for demonstrating quantum advantage, because the 40 qubits, 100 qubits, I mean, that's not, those qubit numbers, if you just look at them, that's not very high compared to what we've just seen at IBM and Google and so forth. And so if you just kind of concern yourself with the number of qubits, not that you should, but if you only count the number of qubits, then now this sounds like really nice targets for demonstrating near-term quantum advantage. And so, in this direction, our group has done taken a number of approaches toward trying to come up with ways of modeling these chemistry systems on quantum hardware. So both of these in kind of the VQE, VQA type setting. So this is a DAP VQE, which Sophia gave a really nice talk about yesterday. And then something that she didn't get to was this control VQE. And in the ADAPT VQE, the basic idea is that you are going to variationally optimize a circuit to minimize the energy of whatever Hamiltonian you're interested in, but that you dynamically construct and define that circuit based on information about the problem at hand. And so it's a problem-tailored approach. In control VQE, what we aim to do is to recognize that even with this kind of dynamically defined quantum circuit, you're still running out of steam. You still have a ton of gates that are needed to be able to implement that state preparation. And so what you could do is then instead recognize that every time you apply a gate to a quantum circuit, what you're doing is you're hitting it, like if you're talking about a transmon device, right? You're hitting it with a microwave pulse. And so instead of optimizing over those different kind of predefined pulses, just directly optimize the pulse shapes by minimizing the objective function at hand. Now, one thing that's nice about that is that automatically encompasses all existing VQEs, because every state preparation gets implemented as a sequence of gates, and if we're optimizing over pulses, then any other ansatz would be a subset of this approach. Now, hiding in the details is that makes this optimization very disgusting. Optimizing these pulses is very hard, and so that's kind of some of the main work in improving and pushing this approach forward. But these are two approaches that we've been working on, both my group, Ed and Sophia's groups, Ed Barnes and Sophia Kahnemoon. And so,
question?
Yeah.
So regarding that, what's the idea here again? Are you increasing the set of calibrated gates that you're going to use? And you're kind of choosing them beforehand, relative to the objective function you're trying to.
Yeah, no, that's a good question. So it's simpler than that.
Dynamically on the fly, obviously.
So what you could imagine doing is then just removing the abstraction of a quantum circuit altogether, because if you're in a VQE setting, you don't actually care what gates are there. You don't care about the logic. You don't care that each one of those gates is associated with a particular logical operation on a quantum state. It's just a tool. It's a tool for taking you from one state to another state. And so if you recognize that we don't care at all about those gates, then what you can do is just recognize that we'll just step back and just go over to the AWG and start turning the knobs and optimizing over the microwave pulses that hit the device, because that's going to implement some unitary. It's going to drive the state from some input state to a new state, and then when we make a measurement of the molecular energy, we can determine whether or not that change in our pulse shape was good or bad. And then we use the variational principle on the molecular energy as our cost function to determine how to shape the pulses. And if you think about why that might be advantageous, is that whenever you're doing a gate-based state preparation, you're searching over a subset of unitaries that have a particular decomposition into two local unitaries. But that's a small subset of the actual full set of unitaries that you could realize within your coherence resources. So if you allow yourself to just start implementing n-qubit unitaries, now you can, the range of states that you can reach increases vastly. Now, it's also hard to optimize, and so it's hard to do it in practice, but I think, yeah, it's hard to tell, but I mean, so in some sense you don't care where you are, because all you want to do is just kind of minimize that cost function. So, so yeah, you can take a look at these papers. We've kind of demonstrated it first here, and then more recently we demonstrated that, as you start optimizing these pulses, right, you have the opportunity, these are transmons, to push the populations outside of the computational subspace. And so this leakage that you generally kind of think about trying to avoid, because it's detrimental and very difficult to correct through like an error correction type procedure, sometimes can be advantageous. And we have kind of some description of why that's the case. And if you want to talk about more about it afterward, then I'd be happy to. But yeah, thanks. Any other questions? So okay, if you're interested in any quantum computing stuff, I guess ask now, because then this next slide is then moving away and never coming back. So just speak now, forever hold your peace. All right, great. So, okay, so let's say that you're doing this. Raise your hand if you've been working in quantum computing at all. I'm just curious to see. Okay, yeah. So I don't need to emphasize too strongly how difficult it is to kind of like build a quantum computer and like run a calculation on, right? Like that whole endeavor is mind-bogglingly. Is that a word? It is insanely complicated, right? And how frustrated would you be if you spent all this money and you ran this quantum computation, and then it turned out to be something you could solve easily on a classical computer. And so what you want to do is make sure that the problems that you're targeting in a quantum setting are actually difficult to solve. And so from using chemical intuition, we know that not all of the active spaces that we could construct are equally difficult to solve. And so how would you determine the difficulty? Well, it kind of arises from the Hamiltonian that you have, the active space Hamiltonian that you're working with. And it's this 2-electron component, which is really responsible for making a problem hard. And so what I want to do is kind of explore a couple different kind of scenarios where this 2-electron integral has some structure that we can exploit to come up with kind of useful classical approximations, and we can talk about them in turn. Okay, so the simplest approach, or the kind of simplest setting, the thing we run into most, is the scenario where the 2-electron integral tensor just happens to be small. So it's not much of a structure, it's more of a magnitude, right? The overall qualitative features are dominated by 1-electron physics. And that's because this 2-electron part is small compared to the 1-electron part. And so what that means is that the understanding the chemistry is really a question about understanding the 1-electron behavior. And that is almost the norm, especially if you're in low energy, near kind of equilibrium geometries of your nuclei. That's what gives rise to, if you think back to like when, most of you probably took chemistry at some point, right? So do you remember molecular orbital theory, MO theory, like MO diagrams? Yeah, like that's where all that comes from. The MO theory is a 1-electron description of the chemistry. And so if this were to go to 0, MO theory would tell us everything that we need to know. But this is not 0, and so it's an approximation. But if this is small compared to this, then we can use it as an order separation, and then do an expansion about this, so that we have some perturbation theory, some couple cluster hierarchies, and we can do a lot of damage just kind of exploring these traditional approaches. And here's just like a picture of a molecule that you might imagine being weakly correlated. It's just a bunch of carbon-carbon bonds, carbon-oxygen, carbon-hydrogen bonds. Like nothing's really kind of partially broken, no transition metal compounds. It's relatively easy. Now, if we had a strong correlation, when I say strong correlation, I mean that this 2-electron integral tensor is now large compared to the 1-electron part, such that the qualitative features of the chemistry or physics are determined by the 2-electron component. And so if that's the case, you have strongly correlated systems, and now you can apply these weakly correlated kind of techniques. However, if the 2-electron integral tensor has some structure that you can exploit, like maybe it forms kind of like a low-dimensional network, like a tree tensor or something, or like a tree network, then you can kind of map that network onto a tensor network representation of the resulting wave function, and make a lot of progress in that, right? We know that for one-dimensional systems, a matrix product state is extremely effective for describing the low energy states. Then we also have PEPs and tree tensor networks, and so if you can map the 2-electron integrals onto some kind of low-dimensional structure, then you can make a lot of progress using tensor networks. Okay, and we just heard a very nice talk from Paul talking about how we can use matrix product states and for global updates and whatnot. So in addition to these types of cases, there's this other type of simplifying structure that I'll talk about, and that's really going to form the basis of the rest of the slides, and that is clusterability, meaning that maybe the 2-electron integral tensor could be large, it could be strong, but that it is localized into pockets, meaning that the 2-electron integrals interact more strongly inside of a group than between groups, meaning that you can kind of organize the molecular orbitals into what I'll call clusters, and then treat the system locally, and then it's kind of perturbative or weakly interacting between them. And that's what I'll call clusterable. And here's just a image, something that is surprisingly clusterable. I don't know if I'll get to talk about that system or not, but But the basic idea is that this kind of is somewhat natural. It doesn't rely on any kind of network structure, so you can have some kind of dense 3D system that you're starting with. But it really kind of relies on the fact that you have some local character in your system that is retained as you go to the global, as a description of the global system. And I'll talk more about this in a second. Okay, so let's say that you've gone through the checklist and you've looked at all of these systems. You've looked at like other simplifying features that you could come up with. And there's no obvious feature that you could exploit to come up with a classical algorithm. And so at this point, then maybe it makes sense to then now start thinking about trying to apply that to a quantum computer. Okay, but like I said, I guess I lied. I said I wasn't going to talk about quantum computing anymore, but that's the end. Okay, so that's the last time I say quantum computing in this talk. So I'm going to talk a bit more about techniques for dealing with these types of clusterable systems and focus only on those. Okay. So as an illustration of what I mean by clusterable, we can take kind of like this extreme example of like a benzene crystal. And here we have a molecular crystal, which is just a bunch of benzene molecules. If you don't remember, is just the hexagon molecule, right? Like, so these are non-bonded and they're just stacked and weakly interacting with one another. And so, even the way I describe it, right? It's a system of stacked benzene molecules. That language implies that this has some local character of being a benzene molecule, even though it is a single large quantum system. All the orbitals and electrons here are interacting with all of them everywhere, right? The Coulomb operator decays very slowly. So everything is interacting. It is a cohesive single quantum system. However, we would think about it and describe it and characterize it in terms of its local character, these single benzene monomers. And so, even though these orbitals are all interacting, this cluster character is retained. And let's say that we wanted to compute the exact diagonalization of this molecule. We wouldn't be able to do it, right? It's big. But let's say we even kind of like backed off and we said, okay, well, I know that most of the kind of interesting characteristics of benzene occur in that pi space. The electrons get delocalized about those pz orbitals. And so now we have 6 orbitals on each one of these benzene molecules. And so let's say I wanted exact diagonalization only in that active space. That's going to be 60 orbitals. It's still far beyond what we'd ever be able to do with exact diagonalization. However, it doesn't. We don't really want to think about it in terms of 60 orbitals. We want to think about it as 10 clusters, 10 monomers, because that's really where the most natural representation arises. So what we want to do is not only be able to define a representation which retains the local information, but we want to have an approach that allows us to compute in that representation, solve wave functions in that representation, and that's what I'm going to be talking about. Does this make sense? Do you understand what we're trying to do? Okay, great. Okay, so the basic strategy is to start off by identifying clusters of strongly interacting sites or orbitals. And so here's a kind of a couple examples of types of systems that you might want to apply this to: collections of chromophores, transition metal atoms, spin coupled to one another, different types of systems here. And so, generally this is tedious, but we can start to automate it. Graph theory, graph clustering approaches. We have some techniques on AO project. There's different ways to go about doing this, but that's not really the bottleneck. So I'm not going to talk too much about how we go about doing this. But once we've taken our large active space and grouped it into, n disjoint groups, which I'll call clusters, then what we want to do is now define a global basis for the entire Hilbert space as a tensor product basis of locally entangled states. So we want to define a set of cluster states. And does anyone do measurement-based quantum computing? Sophie always gets mad whenever I say cluster state, because that means something, apparently. And so when I say, I'll try to avoid saying it, but if I say cluster state, I'm not talking about any kind of resource state. I'm talking about a local eigenstate inside of a cluster. Okay, so what we're going to do is kind of go through, visit each one of the clusters, diagonalize a local Hamiltonian so that we get kind of locally entangled states. We're going to take tensor products of, all possible tensor products of these local states to rebuild our Hilbert space and now work in that tensor product basis. So, this doesn't do anything in terms of the complexity, right? Because we've taken our Hilbert space of dimension 4 to the n, and we've just changed the basis. We haven't reduced the number of degrees of freedom or anything. Well, we can in this step, but we don't have to, right? This is just a unitary transformation on the basis, but it's done because we are doing this to increase the sparsity in our low energy wave functions. And the reason this, the intuition guiding this step is that by diagonalizing local Hamiltonians, we're wrapping up a lot of the entanglement and correlation into the basis states themselves so that the global wave function in this tensor product state basis doesn't have to now account for that. And so now we can increase the sparsity of the global ground state in this basis. Does this make sense? Okay. So far now you could imagine how we might go about trying to construct an approximate approach here. We have a basis now that's kind of folded in a lot of interactions into the basis states themselves. And so I'm arguing that our low energy states have higher sparsity in this basis. So then you say, okay, well, we'll diagonalize the full Hamiltonian in this space and then delete the small components. But that requires you to diagonalize the problem, and that's not going to work, right? Because we have to diagonalize this full Hamiltonian. So what we'd really like to be able to do is have an algorithm that allows us to assume that there's going to be sparsity, and then start from the ground up and discover the sparsity without ever touching non-zero values. And that's the path that we would need to take to make this a computationally efficient approach. Does this make sense? So the way that we can go about doing this, the way that we can discover that sparsity pattern from the ground up is using something in chemistry that we call a selected CI algorithm. Selected CI is something that has existed since the 60s, but has always been done in a Slater determinant basis or even a configuration state basis, but never in terms of kind of correlated basis states, many body basis states. And so we're not the only ones working in this type of approach. Our work is most closely related to Toru Shiozaki's active space decomposition. And then we also rely on Gus Gasseria's cluster mean field as our starting point. And then there's a few other approaches that kind of operate in a similar tensor product state type representation. Okay. So what I'm gonna do is start by kind of describing in detail how we go about constructing the locally entangled states, and then talk about how we work in that basis, and then show you some results. So how we go about defining the local cluster basis is relatively simple. We just use a variational principle. We assume that our wave function is going to have a product state structure, so it's going to be unentangled. And now notice that when I say product state, I'm not talking about a typical bit string that you'd encounter in like if you're thinking of Slater determinants or quantum computing. It's not a product state in that sense, but it's a product of two entangled states. This is a state acting on cluster A, and this is an entangled state acting on cluster B, and we're just assuming a product state between them. Yeah?
Are they anti-symmetrized too, or no?
This is a normal tensor product, not a wedge product. So we're not dealing with any of the anti-symmetry in the representation of our wave function. This is like an occupation number representation. The operators are going to carry the anti-symmetry of the electrons. Does that make sense? Maybe whenever I compute the matrix elements, it'll become clear how the anti-symmetry gets accounted for. Is that but it's very similar to how you would write out an occupation number vector.
Just second quantized expression.
Second quantized. The operators are carrying the anti-symmetry. Does that make sense? After we do the matrix element, ask again if it still doesn't make sense.
So the occupied orbitals in A and occupied orbitals in B, when I swap them, will I get a negative sign or no?
Yes, because they would be created by, the way you would swap them is by applying an operator. and that operator has to commute. Any operator acting on B has to commute or anti-commute through A. And this is comprised of a whole bunch of Slater determinants. Now, so maybe I see why you're asking this question. One thing that works out quite nicely in the way that we're defining this is that the cluster's states in A and B all are eigenfunctions of particle number and SZ symmetries. So this means that we can easily figure out what the sign is as we anti-commute operators through clusters. And that's really important. Now, we don't impose this. It comes out naturally from what I'm about to show you, which is pretty nice. So what we can do is say that we want to define a set of cluster states for this task of defining a basis for Hilbert space that incorporates correlation into the basis vectors. So what we'll do is define some Lagrangian, which has the energy, right? This is the expectation value of the Hamiltonian with respect to a trial product state, and then some orthonormality conditions. And if we make that stationary with respect to, say, cluster A, then what we have here is this global Hamiltonian H, essentially projected and tracing out cluster B. So this gives us an effective Hamiltonian acting on cluster A, so it's a small Hamiltonian, but it's dependent on the ground state of cluster B. And so whenever we diagonalize this Hamiltonian, we get eigenvectors of this. Now this is the energy for cluster states on A. And now the eigenvectors of this effective Hamiltonian become our basis for cluster A. Okay, but then you can say, well, when we go and do that for B, now it's going to change the states B, and so yeah, it's self-consistent. And so if we have n clusters, then what we end up getting is a set of n coupled eigenvalue equations, where each cluster, so this is for cluster A, cluster B, and so forth. And so what we have to do is then we construct this mean field operator. This is the analogous operator to the Fock operator in normal Slater determinant-based quantum chemistry. Now, instead of describing the mean field interaction with kind of single like a single Slater determinant, now this Hamiltonian is describing the mean field description of a whole bunch of different full CI wavefunctions. That's one way to think about this. And so we go through this and we just kind of iterate this until self-consistency. At self-consistency, all of the eigenvalues now become equivalent, and the ground states become equivalent, and it's converged. Right. So this is how we define the local cluster basis, and this is nice because it satisfies a stationary condition. If you're a quantum chemist, or a classical quantum chemist, then the term Bruyon's theorem kind of means something, and we have a weird kind of generalization of a Bruyon's condition because of this self-consistency cycle. So there's a kind of lot of nice, which has implications for perturbation theory and so forth. So there's a lot of interesting kind of ideas and connections to traditional quantum chemistry by starting in this representation. However, in addition to optimizing the cluster states themselves, we also make the energy stationary with respect to orbital rotations that define the clusters themselves. Right? If you remember the first part, we said we're going to identify these orbitals form cluster 1 and these orbitals form cluster 2, but that means that your results would be dependent on the person who chose those orbitals, which is far from ideal. At this point, now what we do is we actually make the energy stationary with respect to fermionic rotations between the clusters. So now the definition of the clusters themselves is fixed by a variational principle. And so it has, again, another set of nice properties that arise from this. So if you think about what this means in practice, we're essentially doing a whole bunch of coupled CAS-SCF optimizations, which is a pain. But luckily, it's not the bottleneck, right? It's not the biggest pain in the neck. We're about to run into that.
Yeah. So here, do you implicitly assume that there is no partial charge transfer between?
Oh, sorry. Yeah. So great question. So Junho's question about like anti-commutation. Anti-commutation, like if I move an operator that's going to act on cluster B through cluster A, it has to anti-commute. Now, if this has partial occupancy, that's a headache. Probably the best way, and I've written a code that does this, but the way that you would do that is, at least the simplest way to do it is just work in a Pauli basis, do a Jordan-Wigner transformation of all your operators, and then you just have a bunch of Z's that hit this, and you have to take an expectation value. But we don't need to do that, because as you minimize this, the way that this this effective Hamiltonian here, the way that this works out is that you have, right, let's say that you're forming the contribution to the Hamiltonian acting on cluster A, and let's say there's only one other cluster. So it's dependent on cluster B. The only term that survives is something like this. So I'm going to say P and Q act on cluster A, R and S act on cluster B. And so we're going to have so this is a term that couples cluster A to cluster B. It's particle number conserving in each cluster. So as I go and I take the expectation value of this operator with respect to B, what happens is that I have to put an expectation value around this whole thing. This is the only operator that acts on cluster B. So then this becomes a density matrix. This is the one particle density matrix on cluster B. So you end up contracting that with your 2 electron integrals, and then you have an effective one particle Hamiltonian that adds to your local cluster Hamiltonian. And that's particle number conserving. So there's never any particle number violation in this. Now, when I first wrote this out, I was like thinking it was a restriction. So then I wrote a very general CMF code that takes all possible things. It just worked with Pauli strings and stuff. And so then I would start from things that had like symmetry, particle number violation, partial occupations on each clusters and stuff. And variational minimization all remove that symmetry breaking. It always collapses down. And then I look and Gus Casaria had commented on this in his paper that this is actually a guaranteed feature of the mean field thing. So, but only for repulsive Hamiltonians. If you had an attractive Hamiltonian, then I think you can break symmetry. But I never work with those. Yeah.
I think you'll interest in the future, but what is the ballpark number of orbitals for each cluster?
So far it's been, let's say, let's think about what types of interactions you might include inside of a cluster. Let's say that you're breaking a bond.
Oh, I mean the number of orbitals.
Yeah. So let's say we're going to break a bond. Then the minimal number you need is 2, right? A bonding and an antibonding. And at that point, your cluster can actually break a single bond. Now, if you wanted to put the triple bond of nitrogen, then you could have 6 orbitals in a cluster. Or in the previous case, right, for the benzene, right, you could have the full pi system, which would be 6 orbitals inside of a cluster. If you think about that from what type of interactions this CMF wavefunction has, that has simultaneous hextuple excitations on all clusters. So it'd be a subset of CCSD, whatever, up to 6 electron excitations. But the largest calculations, I think the largest clusters, we've kind of gone, I think, to 12 orbitals, which would be 24 qubits in a cluster, and diagonalizing over that. Now that becomes expensive.
So you'll just do exact diagonalization, at least within the cluster.
Yeah, so everything I'm going to talk about today is all the clusters are always treated with exact diagonalization. So this eigenvalue problem is solved exactly. Now my student Nicole, she's just she's just written her own RAS CI code for the purpose of approximating that diagonalization by doing like a RAS CI inside of a cluster to cut down on the complexity of that, so we go to larger clusters. But yeah, that's a good question. Anything else? Any other questions about this? All right. So this is how we define the local eigenstates inside of each cluster that we're going to now take products of to form our basis for Hilbert space. Okay.
That's getting a little late, but okay.
Oh, is it? Oh, okay. All right. Well, okay. Huh?
Won the competition, I think.
Huh?
Did I 11?
11.
How far did you get? Okay. Okay. So but this is good. I can do everything I need to do in. I have what, 10 minutes?
Well, it's supposed to be question time, but okay.
Okay. So now I want to explain exactly how we go and discover that sparsity, and I'll just show you with a picture. So what we're going to do is represent our basis states with this type of cartoon here, where we have this for an example system with 3 clusters. You know, this is where we have the ground state on each cluster. I color the states with different colors just to indicate they have all different particle numbers. They have well-defined particle numbers inside of each one of the states, but they all vary. And so, and then we take a tensor product of these. So what we're going to do is start off with some kind of starting point, which is a p-space. So it's a subspace of the full Hilbert space in terms of just a handful of these tensor product states that we deem important. It could just be the ground state, or it could be some selection depending on what you want. And then we're going to build the Hamiltonian in this variational space, which is going to give us a matrix. So in this case, if we literally had 3 tensor product states in our p-space, then we would build the Hamiltonian as a 3x3 matrix and diagonalize that. That's going to give us an estimate for the ground state, or the lowest n states that you're interested in. And then we're going to take that ground state, and we're going to apply the Hamiltonian to that ground state. This is going to now couple to tensor product states that lie outside of our p-space. And then we can use perturbation theory to estimate the coefficients that these would have, determine whether or not they're larger than some threshold, and then if the perturbative coefficients of these external space tensor products are larger than some cutoff, user-chosen cutoff, then we add them into our variational space. The variational space now grows. We build the Hamiltonian in this larger space, we diagonalize, and we repeat the process. And so we keep applying the Hamiltonian to the ground state of our variational space and add every new configuration that's greater than epsilon, and we continue this until it stops growing. At which point we're kind of self-consistent between our variational and our perturbative spaces, and this gives us an estimate for how to converge. And so in the limit of a small epsilon, this now becomes exact. And this gives us a single kind of user threshold so that we can balance computational cost and accuracy. This is exactly the same thing that's been done for years, but in a Slater determinant basis, whereas here we're doing it in a tensor product state basis. Okay. I'm going to skip over a bit how we actually compute the matrix elements. This is a bit complicated. We have to break it up into all the different 1, 2, 3, and 4 body terms, and then kind of organize our operators. And Junho, this is where the antisymmetry shows up. This is a -1 that gets taken into account where this chi is a product of all the occupations in the, or sum of all the occupations in the clusters between I and j. But we don't need to do any computation to actually come up with that. And then the matrix elements, now the key point to take away here is that the matrix elements between 2 tensor product states that go into forming that variational Hamiltonian, or the Hamiltonian in our variational space, the matrix elements themselves are expensive to compute, unlike in a Slater determinant basis where they're just lookups from a table. Here, we have to do tensor contractions between local representations of fermionic operators in our many-body basis. So we have to do tensor contractions with our 2-electron integrals to evaluate a single matrix element. So that's super expensive. But the hope is then by the reduced dimensionality, by folding all those interactions into the basis themselves, we come out ahead. And in the calculations that I'll kind of skim over, we emphasize that we do. So here's an example of a 4-body term, which is kind of the most expensive part. So we have a code that kind of automatically assembles these matrix elements. Yeah? No, everything's orthogonal. Our tensor product state basis is perfectly orthonormal, so we have no numerical problems from linear dependencies.
I see. So it's very different from internally contracted.
Yeah. So now I've thought about trying to use some ideas from internal contraction to try to make this a bit more efficient, but I haven't done anything yet. Yeah. So, but we don't have any problems with orthonormality.
Okay. It's more similar to tensor network concept.
Yeah. So it kind of works in the many-body basis like a tensor network, but it doesn't rely on any kind of network structure, which is good and bad. Like it doesn't have the efficiency afforded by that, but it also doesn't depend on.
So you
this.
assume like all the entanglement between clusters is 0.
At
least
or
for the
small.
wave function answers.
Yeah, yeah. So, so this is kind of what the code does. It just goes and collects these things from memory and then contracts them as needed for the thing. So here's some numerical results, kind of just illustrating this kind of motivating example for this 60 orbital, 60 electron case. What you're seeing here is, and I'll show you a couple of these plots. I'll flip through them a little bit quickly. So these are variational numbers right here. So what I'm going to do is I choose an epsilon, so a cutoff, and then I compute a variational number. And then I do PT2 correction, a perturbation theory correction on top of this, and I get this number. And then I'm going to do the calculation again, but I'm going to tighten that epsilon. And that means my variational space is going to increase, which means my energy decreases. And then I do another PT2 correction. And I do it again, and then again, and again. And then what I find is that if I plot the variational numbers against that delta PT2, the perturbative correction, if I plot that against it, it becomes very linear. And this is identical to what's done in the Slater determinant type computations. So I can then like just extrapolate out to 0 PT2 correction and get an estimate for the exact diagonalization. Now the distance from your best variational number and the extrapolated point kind of gives you an indication of how far away you are from being converged. In this case, right, these are millihartries. So this is from here to here is 1 millihartry, which is often the kind of accuracy you're looking for. I mean, we're like microhartries away from converge. So this works quite well for these systems, but it should work well in this case.
So does it mean PT2 over the tensor product state? Or
Say it again?
PT2 correction on top of tensor product state?
Yes, it's a PT2 correction on top of the best variational number. Yeah. So, but we can also apply it to things that you might not immediately think of as being clusterable. Here we have this diiron compound where we have a 26 orbital active space, and we have 5 unpaired electrons on each iron atom. So we put a cluster here, here, and the bridging oxygen. And as we go through, we compute the lowest energy, the 6 lowest energy states. So this is the singlet, triplet, quintet, heptet, nonet, and 11net. And we see this. I mean, this is extremely converged as we see in our extrapolation. And so we can then pull out the J coupling constants and all of that stuff from these types of calculations. One thing that's probably even more interesting than the quantitative behavior is that we're working in a basis of iron wave functions as opposed to just single particle wave functions, which means that these are highly interpretable representations. What we can do is we can project these kind of near exact solutions onto as single basis states. So these are just different spin orientations. And we can then build an effective Hamiltonian that lives in this 6x6 matrix. So if I diagonalize this 6x6 matrix, what I'll get is the exact kind of diagonalization. Now, I can also then start to analyze this and play around with it. So I could build these matrix elements in the raw tensor product state basis, and I get these matrix elements. So this is negative, this is positive going down to negative. And if I diagonalize this raw Hamiltonian in 6 different spin orientations, I get a ferromagnetic coupling, which is qualitatively wrong. But now if I go and I take my exact TIPSY, or near exact TIPSY calculations, project it and form an effective Hamiltonian, I now get matrix elements that are dressed by these interactions. And now we see the proper qualitative and quantitative behavior emerge from this simple and interpretable 6x6 matrix. So in addition to having these quantitatively accurate results, we also have, now it's time. So we also have this interpretable representation. So thank you for your questions so far. You kept me from running out of slides that I didn't finish. But this is pretty much the story I wanted to get through, explaining the way we define the basis, how we discover the sparsity, and we have a couple other systems where we've kind of applied it to, but more data, it doesn't really change the story much. So I don't know if there's time for any other questions, I'd be happy, but otherwise we can talk in the break.